So do we have any questions on the previous lecture and the bolt strength? All right, let's proceed. So this table here is available for Shear, and it's gonna be for almost all bolt size that you're gonna be working with. And we have here a good note.
Excuse me, sir. Sorry to interrupt, but I just wanted to ask that is the exam on Monday or Wednesday? Because the schedule says it's on Wednesday.
Wednesday.
Okay, thank you.
Wednesday, no problem. Any other questions? We're good? All right. So Monday, we're gonna have the review. Wednesday, we're gonna have the exam. So I like these notes here because in the previous version, we didn't have any of them. So this, some notes that they put here is very, very good.
يقول اختبارنا الأربعاء أنا فاهم غلط.
Excuse me? Okay. So we have here a good footnote, and it shows exactly what does mean by each group. That was not there in the past, in the previous version. So you start with it. Because all of a sudden, we used to have here A325, everything was just indicated here in this box. All of a sudden, they took it out, they put just group A, B, and C, or just group A and B. Now you need to go back to a different table, figure out what does mean by group A or what does it mean by group B, and go to the explanation of it in the code section itself. But now it's good that they put this notes here. But I decided also to add this. So in my steel book, I put this kind of notes in pencil. So I have the hard copy, and I just added this notes next to it so that I don't forget what size or what grade I'm going to be using here under group A or B or C. Also, we have another table. So this table 7.1 for the available shear. This here table 7.2 for the tension. And in the tension, as you see here, there is no X and N condition. They are all the same. So in here we have N condition and X condition, as you see it here, N and X. But in here we have it all for just one type of tension, force, strength. There is no two categories like what we have in the shear. Again, the reason is because when you apply tension here to the bolt, the tension is going to be going through the threaded sections anyway. So it doesn't matter whether you have N or X condition. Again, for each bolt group, I put here the kind of the famous designation or the SCM that you're going to be seeing there, right next to it in red. Also, they have the same note here, which is very good. Also, the good thing, they put the phi factor. So some people will say, maybe in tension, phi factor is going to be different. Phi factor shouldn't be like 0.9 versus for the shear is going to be 0.7. You're going to say, this is not correct. Phi factor is going to be 0.7, whether you have the bolt in tension or you have it in shear. I'm going to take you back here, a few slides. I'm going to take you here to this equation. When you look at this equation, it says nominal strength. It doesn't say shear or tension. So this applies here for both. And this 0.75, which is a phi factor, applies for tension and for shear. So it doesn't matter what type of force. That's what we're talking about here. Now, in order for you to do bolted connection, you need to drill some holes in the steel plate or steel angle or W section. And here's the nominal size for the hole dimension. As it says, I'm sure that you have seen this in the past when we were talking about tension members, and we are going to be going usually with standard connection or the standard hole. And as a kind of rule of thumb, you just take the diameter of the bolt and then you add 1/16 of an inch to it. So if you like to figure out the hole size, you add 1/16 of an inch to it. Look at this one here. Half an inch means 8/16. The standard diameter for the hole is going to be 9/16. 5/8 is going to be 11/16 because 5/8 means 10/16. There's another connection here, another hole size that we call here oversize. This oversize, you can use it in base plate. If you have a base plate of a column, some foundation, you can use this. If it's going to be only for gravity. But if you have a beam connection, another beam or a girder is going to be the standard. We have some also the slotted connections or slotted holes that we're going to be talking about later on, but we don't really need it at this point. So bottom line, rule of thumb, is give you the diameter of the bolt plus 1/16. Lots of people may think it's going to be 1/16 from each side. means that the hole size is going to be the bolt size plus 1/8 of an inch. So I want to correct this. It's going to be the bolt size plus 1/16, which means 1/32 from each side of the bolt. So here's a bolt, let's say, or let's say this give you the hole, and this will be the bolt size. Can I put it right here? Can I say maybe roughly like this? Consider this to be a circle. So this distance, the difference between the two sides from here to there is going to be 1/32, which means 1 divided by like this. This is going to be the size of an inch. This is going to be the length from each side of the bolt. Also, we have this minimum edge distance. Now, for now, we are not clear what does mean by edge distance, but it gives you here the bolt diameter, and then it says a sheared edge and on the other edge. So I'd like to know what is the sheared edge, what is the other edge. This gives you the other edge, but this one is called the shear edge. So let's go through this. I'm going to go here quick. Just move here to this example to understand what does mean by sheared edge. As you see here, tension forces can be running this way, which means this angle, you're trying to pull this angle in this direction. Now, this side or this distance give you the sheared edge because you're trying to shear it off. You're trying to cut off this piece, right? So that the bolt is going to be coming out. You're going to pull this angle to the right, and this give you the sheared edge. So the shear distance or the sheared edge distance is going to be here equals to 2 inches. The other edge distance is going to be from here to there. And as you see here, if this angle is 4 by 4, this also just happened to be the same as 2 inches. So this is here explains to me what does mean by sheared edge versus the other edge. Okay.
Sir, does a bolt have to be within shear edge in order for it to fit? Or if the bolt is out of the shear edge, will it be safe?
You need to provide this distance, otherwise the connection is not good. So for example, if you look at this size here, this bolt, as it says here, how big is this bolt? 3/4 of an inch. Let's see what the code says about the edge. The shear edge for 3/4 of an inch, it should be at least 1/4 of an inch. I provided here 2 inches, so this is good. My connection is good. If this had been 1 3/4 of an inch, I'm gonna say, well, still okay. Once you go to 1/4, it's gonna be very tight, not acceptable. So practice-wise, usually if you have 3/4 of an inch, we provide 1.5 inch for the edge distance. So usually it's gonna be a minimum of 1.5 inch. I understand that from this table it says here 1/4, but in practice, we don't want to go this tight. You don't want to go to 1/8 of an inch because easily you can just go to the job site. All of a sudden you see this edge distance is wrong. Someone cut it wrong. You don't want to replace pieces. So give yourself some room. Even if I have 5/8 of an inch bolt or 1/2 inch bolt, I would really like to see 1.5 inch, at least 1.5 inch for the edge distance. In this example, it says the connection provided in this figure shows an angle and a plate 836. So both of them is going to be 836. The bolt conforms to the ASTM A307. This is like the machine bolt. The connection capacity is nearly equal to. Okay, now I need to look at the connection capacity. I have 2 bolts exposed to direct shear. It's going to be single shear. Reasons because I have 1 plate and 1 angle. So I'm going to have here only 1 surface of the bolt exposed to shear. Size of the bolt, 3/4 of an inch, A307. So let me go back here to my table for the shear and try to figure out for 3/4 of an inch, A307 single shear. You say, okay, 3/4 of an inch, A307 single shear. Where should I go? It's going to be 8 point. It's going to be this number here, 8.97. It's going to be almost 9 kips, if you like. I'm using LRFD, 3/4 of an inch, A307 single shear with this S. So it's going to be this single shear thing. Okay, good. This is going to be for the bolt, just the bolt. How about the angle? How about the plate? I said, well, we have seen this before. We know how to do tension capacity of a plate, tension capacity of the angle. Cross-section area of the angle exposed here to shear as a cross-section area is going to be equal to that area that you can look it up in the table. For the net, you're gonna have here a bolt and a hole, and you're gonna have a critical section for shear, which is gonna be, let's say, right here. So you need to deduct the hole size times the plate thickness or the leg thickness. So for the plate, it's gonna be the hole size times half an inch. For the angle, it's gonna be the hole size times quarter of an inch. Why? Because the leg thickness is gonna be here quarter of an inch. All right. How about the plate width? I'm gonna say the plate width is gonna be equal to 6 inches. Now I have 3 items that I need to figure out the capacity for them. I'm gonna have the angle in tension, and I have 2 equations for that. I have the plate in tension, also I have 2 equations for it, and then I have the bolts, 2 bolts giving shear. For each bolt, I have a strength of almost 9 kips. So I'm gonna say here's the strength of the bolts. 2 times 8.97, roughly 18 kips. I'm gonna be good with this. Now the hole size is gonna be 3/4 of an inch. You're gonna be adding 1/6 of an inch, and then you run through these 2 simple equation that we went through before in tension members. Now the first item that you have the capacity for is gonna be the bolt themselves, and the bolt we have capacity of 18 kips. The angle has a capacity of, let's say, 75 kips. For the plate, has a capacity of 112 or 113 kips. Now, the lowest value of all of the 3 is going to be the weakest link. This is going to be the 18 kips, and this is going to be the strength of this assembly. So the strength now of this assembly is going to be 18 kips. Any questions? All right, let's see the second example. Very similar example that also have seen very similar connection to this. I have here 2 plates on one side and 1 plate on one side. As if you have something like this in the section, you're gonna have 1 plate like this, and then you're gonna have 2 plates sandwiching this plate. You have 1 right here, and here the other one is gonna be like this. Okay, good. Now I have few bolts. I have 4 bolts here connected. So in this case, this is gonna be a double shear situation. It's not gonna be a single shear because I have here 2 surfaces at which I have the bolt is cutting through. So if this is gonna be here one of the bolts, can I have here 2 sections? Here is 1 and here's the second. I have 2 sections here to shear off the bolt. So okay, the bolt size is gonna be 7/8 of an inch, and it says it's gonna be A325X high trench bolts. And for the plates, it says it's gonna be 572. 572 is gonna be 1 plate connected to A36, 2 plates. So I have the same thing. I have 3 items here that I need to figure out the strengths for. I have 2 plates on one side, and for that I should be able to figure out VTN, which means the strength of these 2 plates in tension, and the strength of this single plate, grade 50, in tension, and the strength of 4 bolts exposed to shear as double shear. Okay? Let me look first at the double shear bolts. I have here 325, 7/8 of an inch, X connection is going to be double shear. So each bolt is going to be supporting 61.3 kips. I have 4 of these, it's going to be 4 times 61, I have 245. Okay. The bolts can take up to 245 kips. Let me confirm this again. I have 3 items. 2 plates, they work together as 1 piece, 1 plate on the other side, and then the bolted connection. Okay, I'm gonna be doing the strengths for all of the 3 items, and at the end, I'm gonna be taking the lowest value of all of these values in terms of strength. Here's the plate, the grade 50, and here's the hole size. It's gonna be bolt size plus 1/16 for the net, and you know the entire story for doing tension strength for 2 plates versus 1 plate. So for the 1 plate, the grade 50, the strength is going to be 156. So let me put this in the box. This is going to be the strength of 1 plate, which is on the left-hand side. For the 2 plates, the A36 is going to be 223 kips, roughly. Okay? For the bolts, it's going to be 156. Excuse me, 245. Now, which one is the lowest? Now I need to compare the 3 values. 245 versus 156 versus 223. Now this is going to be the smallest value, and this is going to be the design value that controls the assembly strength. So it is true that the bolts have bigger strengths here, 245, but the lowest value of all the three items, 2 plates on one side and 1 plate on the other side, this lowest value was just controlling the strength of the entire assembly. So I'm going to go with the strength of the lift plate, which means this plate here was controlling my design because it has the lowest strength and tension. Okay. Questions? We're good?
Sir, when we were comparing for the 2 plates, did we take their value as 2 or single or as 1 for each plate?
If you see here at the connection for the 2 plates, right? This is your question about the 2 plates, how we calculate out.
Yes, sir.
Okay, let me go back here one slide. How much is the side here? You know, the width of the plate. It says 7 inch because it says
Yes,
2 plate, half an inch is going to be the thickness times the width, and it's going to be continuous. We don't know exactly where it ends. Distance from here to there is going to be equal to 7 inches times half inch is going to be 3.5 square inches for 1 plate. Okay, now I understand. 1 plate is going to be 3.5. Now look at this. It says 2 plates times half times 7. So this here applies for 2 plates. You see this? It says
Okay,
2
sir.
plates, half an inch.
Okay.
Yeah, so, all right, thank you. Thank you, Manny. Now, when you have a group of bolts, how would you find out the strength of this group of bolts? So I'm going to say, just a minute ago, you showed us 4 bolts. But look at this. 4 bolts was exposed to shear, and it was direct shear, double shear. It just happened to be double shear. Also, when you look at this connection here, that was also direct shear. I don't see here any eccentricity. And let me assume here for a second, if I put some force coming in this direction, would you have any eccentricity on these bolts? You're going to say no. Why? Because one half of the force is going to be going here, other half is going to be going that way. The problem is going to happen if I have eccentricity from the center of the bolts. Now, where is the center of the bolts? If I may just remove this. I don't need this now. I don't need this. I don't need this. Now, where is the center of the bolt? I'm going to say center of the bolt is going to be right here. It's going to be like this, right? If I bring this and put right in the center of the bolt, and also you may call this center of rigidity, if you like. If I bring this here, I'm going to have to split this force equally on these 2 bolts. The problem is going to happen once I start to bring this force right here, like this, for example. If the point of application is here. This means that I have a force coming in here plus a moment. So I'm going to have some rotational. I have some rotational effect. So this bolt is going to be exposed to different force from just one half of this force. Another condition for this, if I'm going to have here the center of the bolts in this direction, now let's talk here about the X direction. Center of rigidity of these 2 bolts, let's say it's going to be right here. If I put this bolt right here in the middle, you can just take this force, split it equally on these 2 bolts. But if it happened that I'm going to be moving this right here, the force, this now is going to be creating a problem for me because I don't have just one force acting on this. I'm going to have this force plus some rotational force. Rotational force, which means moment, is going to be equal to this force multiplied by the distance from here to there. You can say distance from here to there. It's going to be like this. So if you come at this distance, which is a spacing from the center of the bolt to this force, and you call it E. So I'm going to call this E, which means eccentricity stands for eccentricity. Let's say in inches. And this force, I'm going to call it here F. Now, how much is the moment acting on this assembly? You say the moment equals F times E. So we're going to have additional moment rotating the system this way. So in a case like this, you're going to say your moment is coming in this direction here. So I'm going to say, let's say your moment is going to be coming this way. Like this, rotating this way. At the same time, also, I have a force coming here, which means I can split this force or can resolve it into one force. It's going to be concentric plus this rotational, which means some moment. I say, okay, so what does it mean by that? It means that the first bolt is going to be seeing a force like this, and the second bolt is going to be seeing a very similar force, right? This is going to be two shear forces. And to resist this, I'm going to have a force coming this way, and another force coming this way, and they create a column, and each one of these forces is going to be equal to what? So this force here is going to be equal to this moment that I have at the bottom, right? So this force, if you like to call it V, is going to be equal to this moment divided by 3 inches. Now, where is the 3 inches coming from? You can say 3 inches is going to be coming from here, which means this moment resulted from the applied force, F times E, is going to be resisted by a couple. And this couple is going to be equal to V force. And this V, you can just take this V, and here's another V multiplied by 3 inches, which means V times 3 inches equals F times E. The two moments are equal to each other. One moment is rotating counterclockwise, which is applied moment. The resisting moment is going to be applied clockwise. The applied moment is going to be F times E. The resisting moment is going to be equal to V, which means this force or this force times 3 inches. Any questions on this concept? When you have some eccentricity on the bolt from the force? Certainly you can take the whole assembly here and rotate it 9 degrees, right? So if I can say here, if I'd like to take this, just this piece here, and rotate it 9 degrees, what do I mean by rotate this 9 degrees? I'm gonna say, let's say, do it this way. Same concept apply, right? So if you have a couple of bolts or 3, 4 bolts, and then the force is gonna be eccentric from the central bolts, you're gonna have here some additional moment that you apply to the bolts. Okay. Now we have here 2 forces applied on each bolt. I'm gonna be taking this bolt here to do my analysis on. This force here is gonna be equal to V, the vertical force, and this force is gonna be equal to H. So what is the force H? Force H is going to be equal to what? I understand V is going to be equal to M divided by 3. How about the force H? You can see here's H. H force is going to be equal to F divided by 2. Where this is coming from? It's going to be very similar to this concept. When you have a shear force supported by 2 bolts, each bolt is going to be taking a force in the same direction of this F force of F over 2. I said, okay, now this makes sense. Now I have V and F, vertical component, horizontal component of this bolt. So what should I do with them? I'm gonna say, when you look here at the shear strength of each bolt, you need to look at the demand, and the demand in this case is gonna be equal to the resultant of these 2 forces. It's gonna be some force coming this way. What would you call this force? I'm gonna call it here R, like resultant force. It's gonna be equal to what? It's gonna be equal to V squared. If you like, it's going to be square root of V squared plus H squared to the power of 0.5. This is going to be square root summation of the squares of these 2 forces. And this R here is going to be the force that you need to compare against the strength of the bolt, which is strength, the shear strength of the bolt that you get out of this table. So once we have here some eccentricity, it means that we are applying additional moment, and this moment can be resolved into a force like this. So okay, this is good. That was really good. Let's say, how about if I have
Sir, what is H?
H, horizontal component. Yes, as I said here, this F is going to be resolved into 2 components, right? Here's you're going to have an H, and here's H. How much is H? It's going to be equal to F over 2. Okay?
Okay, thank
you. So this H, you're going to have one here and one on the other bolt. How about the V force? V force is going to be the vertical component due to the rotational moment. You have some rotational moment here. You have some moment, acting moment is going to be equal to F times E, is going to be coming counterclockwise. And you have another component is going to be coming clockwise to resist the F times E. It's going to be equal here to V multiplied by 3 inches. Okay? So fine, this is good. That was simple. This analysis was really simple. That I was able to find out this V force because I have only 2 bolts supporting this rotational moment. Now the problem is going to happen when you have lots of bolts supporting this moment. Like in what case? Now let me move forward. Like in here. Look what happened. Look at this solid plate. Don't worry about this dashed thing. I'm going to say here, look at this. Where is applied force? Where is the center of the bolts? I'm going to say center of the bolts, forget about this dash and forget about this dash bolts after rotation. This is going to be the CG of the bolts. So I'm going to say here's the line, right? It's going to be the line, which means center of gravity of the bolts or center of rotation of the bolts, if you like. Now, where's the applied force? I'm going to say applied force is going to be right here before rotation, right? It is going to be roughly here, let's say. And the distance from here to there is going to be equal to E. You see this E? This E is going to be the same as this distance from the CG to the applied force. It's going to be this distance here. So I'm going to come here and call this E. Fine, good. And this force is going to be called P sub U. We called here P sub U, like ultimate loop. This means that you're going to be having here some rotational moment. You have a moment coming this way, clockwise. And you have also a vertical force. Now you have 8 bolts. Am I correct? 8 bolts. Each one of this bolt is going to be exposed to a force. And this force is going to be equal to how much? The vertical component, I'm going to call it here V. V is equal to how much? Can someone help me? P sub U divided by how much?
8.
8. So each one of these bolts is going to see this vertical component. How about the moment? I'm going to say, well, the moment is going to be really tricky. Because for the bolt which is going to be further away from the CG, is going to see a higher horizontal component. I say, okay, for this component, if this wants to rotate this way as an applied force, I'm going to have a force coming like this as a resistance force. But the applied force is going to be coming in which direction? I say it's going to be coming this way, right? Give you applied force, applied force. This force here, you can call it H if you want to, a generic call out for any bolt. You're going to have also another force here. Now, which one's larger? Is this H1 or H2? Let me put here also H2. You say, how about H2? Put it right here. This is going to be H2. Which one's larger here? H1 or H2? Can someone help me with this?
H1.
H1. Because this distance, which is from the CG to that location, this arm here is going to be larger than that for the H2. Look at the one for the H2. It's going to be from here to there. So when the bolt is getting further away from the CG, the force is going to be higher. So H1 is going to be larger than H2. So in this case, I have more than one unknown. When I was doing this simple analysis, I said that that was really simple because I just have 2 bolts going back here. Because the moment I was just able to resolve it into 2 components, 2 forces. And if you like to put the applied forces, you should have put this force is getting this way, right? Am I correct? It has to be the applied force because I put this at the resistance force. Am I correct? So applied force is going to be like this because the rotation is going to be like in here. So applied force is going to be like this. Here's the applied force. This is also the applied force. Like in this case, I put the applied forces. I didn't put the resistance forces. So the force is going to be coming downwards. It's going to split into 8 equal forces. But because of rotation, you're going to end up with different force at each bolt. The other simple example was 2 bolts. That was just simple. I was able to split the force the rotational for the moment and put it in 2 bolts only. But here's going to be more complex. There's more than one theory here to finish this business. One of them, just assume that the center of rotation is not changing, which means if you have a group here of bolt and you start to rotate it, after rotation, the CG is giving the same place. Another method says, no, this is not exact. And if you like to do more detailed analysis, you need to assume that the CG is going to be changing in location. Now the problem becomes more complex, and we don't want to go through this. We'd like to look here what the code offers us, or the steel manual is offering us. The steel book, or the steel manual, has lots of these tables, which is very good to use. Gives you a case like this, and another case if you have 2 rows of bolts, another case if you have 3 rows of bolts. So in here, it shows 5 bolts, but when you look at the table, it says number of bolts, just n. You can have 5, you can have 10, you can have all the way up to 12 bolts in one row. And it says here, if you have 2 bolts, there's going to be some number that you need to look it up here. If you have 3 bolts, 4 bolts, 5 bolts, all the way to here. And the spacing has to be equal between the bolts. So the spacing here, as they say, it can be 3 inches or it's going to be 6 inches. So the spacing here is going to be 3 or 6 inches. If the spacing is going to be 4 inches, you cannot use this table. So this is the reason that usually our spacing is going to be like 3 inches. We keep it usually at 3 inches. And this table is made for 3 inches because you know that people in practice usually use a spacing of 3 inches or 6 inches. So I'm going to say, let's stay here with 3 inches. So I'm going to assume I'm going to have a spacing here between bolts is going to be 3 inch for the spacing, which is nice. I'm going to have here 8 bolts in one row. Okay, what else that you'd like to know? This could be the question. Also, they give me this eccentricity, they call it EX. So I guess you need to have this EX. Where this is going to happen, I'm going to say in this column. So let's assume for a second that this EX is going to be equal to 4 inches. I decide here to go with 4 inches. So I said, okay, I'm going to go here with this 4 inches. I'm going to pick this row here. I said, okay, and you have 8 bolts. Great. And you're working with the 3 inch. This table, not this table, not the bottom table. I said, okay, good. Now let's see the intersection between this. I'm going to say intersection is going to be 6.64. So what is that number? I'm not clear. Is this the strength of the bolt? I'm going to say no. This is going to be number of equivalent bolts. So in reality, how much bolts you have? You put 8 bolts. Number of equivalent or effective bolts in this case is going to be 6.64. Meaning that if you know the strength of one bolt on shear, just take it and instead of multiplying by 6, you're going to multiply by 8, like this number here, the actual number, you multiply by 6.64. They call this factor here C factor. I'm going to say now this is going to be my C factor that I'm going to be using in my analysis. So here C equals 6.64. What is that? Number of equivalent bolts. Now let's see what is written here. This table is say coefficient C. Okay, yeah, this table for just coefficient C. Yeah, any number that you see here is going to be C. And this number is for eccentrically loaded bolt group with an angle of 0. What does it mean by an angle of 0? In the same book, you're going to see some other cases when you have an angle like this, 30 degrees or 15 degrees or 10 degrees. You have different cases. So in this case, this angle is going to be equal to 0. So in my case, I'm going to say it is going to be like this. This is going to be the case I'm going to be working on. Okay, great. P or P sub U is what? This is going to be the available force that you're going to put in there. What does it mean by available force? It means the force that you want to work with, the required. In this case, when you do this R sub N is going to be the capacity. And R sub N lowercase is going to be the capacity of one bolt. So if you know the capacity of just one bolt, take it multiply by C factor to get the total capacity of the bolt group. So I'm going to say here, capacity of one bolt, which means PRN is going to be equal to C times Rn lowercase, also phi Rn. Don't forget the phi Rn. For example, if the strength of one bolt is going to be equal to 10 kips, in this case, I'm just throwing here a number. I said, well, I found out that the capacity of one of these bolts is going to be equal to 10 kips in shear. Let's say in this case, that strength for the entire group of bolts, I'm going to say here, one bolt. I'm going to say phi Rn for one bolt is going to be equal to 10 kips. Great. So what does it mean? Total capacity is going to be phi Rn for the entire system is going to be equal 6.64 times 10 is going to be equal 66.4 kips. It's going to be the group capacity. I'm going to call this here the group capacity. Now I guess I understand why they call this going to be number of equivalent bolts, right? Great. This should be very helpful, especially when you have two rows of bolts and you have the steel bolt. It's going to be so simple. Now I'm trying to compare what happens here to this number of equivalent bolts when I'm talking about this discussion about vertical force, horizontal force, and find out the result and compare it with phi Rn for just one bolt. So I'm going to go back here to my deal or my analysis that I was working in here. Also, I need to flip this here for the applied force, right? I guess I should do this. So in this exercise, right, I did two forces, horizontal, vertical. I did the resultant. I compared the resultant with phi Rn, which means the strength in shear for one bolt. In here, I didn't do it this way. Now let me jump here to my table. I didn't do it that way. What I have done, I have taken the total strength of the entire system here. Now I don't see any horizontal forces. But what happened, the equivalent number of bolts has been reduced, which means inherently, all the effect of this little force is coming this way, right? And another smaller force coming this way. And other forces also, if I may take this down here. Another force is going to be coming like this. And another force is going to be coming this way, right? Have been considered. They accounted for it when they give here this reduced number of bolts. This reduced number of bolts, equivalent number of bolts, consider the effect of the eccentricity. They made it in a different way. Therefore, at the end, when you compare the 6.4, you compare it versus P. You say, here's the demand as in shear, because this vertical force is going to be causing shear on these bolts. So when you compare this phi Rn, you compare it with P, or P sub U, for the ultimate force. All right. There's also another way of doing it, or a different kind of example that you may look at for seeing. Now look at this force here, and look at this E, and look when you look from the face of it. So if you like to look from this side, if you like to see the elevation of it, this side, it's going to be like this. So you have here two rows of bolts. It is true that this is equivalent here to one vertical force. It's going to be causing shear on each one of these bolts, plus some moment. But the moment is going to be coming like this, right? Moment's going to be coming this way. So moment is going to be pushing down at this and causing tension, all of that. So here's going to be some compression, and for each bolt, you're going to have tension. It means each bolt here is going to be exposed to some shear force and some tension force. This connection is totally different from this connection. This connection and also the angle connection, all the forces and the rotation is going to be causing shear on each bolt. Now let me go forward. In this case, the vertical direct force is going to be causing shear on each bolt, and the eccentricity and the rotation of the moment is going to be causing tension on each bolt. Now this is going to be completely different because now we need to do tension and shear interaction for each bolt, which is completely different from what we're doing here. This is completely different issue. This one here, the vertical force and the moment, both of them, they are causing shear on each bolt. But in here, the vertical shear or the vertical force is causing shear on each bolt, and the rotation or the moment is going to be causing tension on each bolt. So two different animals, if you like. When it comes to the examples and our exam and our homework, we're going to be working with this case. We are not going to be doing this, but this is here just provide you for your knowledge if you like to think about it or if you are going to be exposed to it one day. I'm going to look here at this example 5.3. Gives me bolt group, says 5 1/8 of an inch, A490N. So I have here 5 bolts. This spacing is going to be 3 inches, and the eccentricity is going to be 4 inches. I have a vertical force, it's going to be called V. And the question is, how much is the bolt group capacity? Now I need to figure out the strength for just one bolt. So I'm going to have here 5 bolts, right? So just for one bolt, 1 1/8 of an inch, A490N, I need to figure out the strength of it. After I find the strength for one bolt, and this will multiply it times 5, because of the eccentricity, I need to pick a lower number, which is going to be C. So instead of C is going to be equal to 5, C is going to be equal to a lower number. So someone here is going to come and say, you know what? If the force is just happening here, how much is the C value is going to be equal to? Elizabeth,
5.
can you help me with this? Elizabeth?
Yes.
Yes, C is going to be equal to what? If the force is going to be right in the middle.
If the force is right in the middle.
Yes, if the force is going to be right here, not here. How much do you expect for this C value? Take your time. You don't have to rush.
Oh, okay, thanks. All right. So looking at table 7.7, we can see. All right. So the spacing is 3. Our eccentricity is 4, and then we have 5 bolts.
There is no eccentricity now. What I'm saying is, if there's no eccentricity, if the eccentricity equal to 0.
Oh, okay. So then we have, okay, so it's just a direct V. So it's the PU given that either. And that would be divided by 5 for that. Equivalent to the number, C factor is equivalent to the number of bolts. 6.4. It would be equal to the P value, but that's not given, is it? So we would have to get more information of the volts. Let's say it's 1.18 of a 490.
Okay. Thank you, Elizabeth. Thank you very much. Andres, do you want to help me out with this?
Sorry, must I go ahead?
Yeah, do you want to help me out with this? Or you can say I cannot, this is fine.
I'm also looking through the book as well.
Okay, you don't know what we're talking about, right?
I'm just guessing here, but would C just be equal to 1?
1. What does it mean? Are you saying that all of these bolts, the equivalent number of bolts here is going to be just equals to 1? Is this what you're saying?
No, because I'm just looking at the Rn is equal to CRN.
Okay, you're looking here.
Yeah.
Good. Do you understand this table?
The C is a modifier for the group action, right?
Yeah.
But if there's no eccentricity,
Would it be equal to the phi little rn of the bolts? So the 50.7?
So let's look at this. Let's try to understand this table more. Because the answer I'm receiving here means that the point is not clear. This C here means if you have 4 bolts and you have some eccentricity of 2 inches, you cannot really count them to be 5 bolts, right? Or if you have 5, you cannot really count them to be 5 bolts. They're going to be slightly less. Why? Because the effective eccentricity. You're going to have an effective number of bolts is going to be 4.39. When the eccentricity here is getting larger, what happens to the effective number of bolts? It gets lower, right? See what happens? This effective number of bolts, you're going to put there 5 bolts, but because of big eccentricity, they're going to be equivalent to, let's say, 1.4 bolts. Okay. If I have 10 bolts and the eccentricity is going to be only 2 inches, now I have lots of bolts here, small eccentricity. Instead of having 10 bolts, I'm going to have 9.53. If I have no eccentricity at all, the effective number of bolts is going to be equal to number of bolts. You'd like to see an example. I'm going to take you back here to this one. In this analysis, when we have done it, we said that each bolt here is going to be taking 1/2 of the force when the force was right in the center. Say, okay, here's the way we have done it. We just say that the capacity is going to be equal to number of equivalent bolts times the strength of 1 bolt. So this actual number is the C factor. So I can put it right there. I'm going to say this number here is going to be my C factor. C equals to 2. Why? Because I have no eccentricity. When you have no eccentricity, there is no reduction in number of bolts. Let me go to this example here. I have 4 bolts. The force was right in the center. It was split evenly in these bolts. So now let me look at the strengths of these bolts. It says here, PRN is going to be equal to C, so I'm going to say in this case, C equals to 4. I have a total of 4 equivalent bolts. And in reality, I have 4 bolts. The reason that I don't have any reduction is because this force is concentric with these 4 bolts. I said, okay. What happened here in this case? I have 8 bolts. I have some eccentricity. So the strength is going to be reduced. Why? Because the horizontal forces that you're developing here is going to be eating out a little bit of the strength of the bolts or the bolt group. Instead of having 8, because this eccentricity of 4 inches, I'm going to have 6.64 bolts. So your C factor is going to be 6.64 times the strength of 1 bolt is going to be 66.4. Okay, now I'm clear, I hope. I'm going to be coming to this example that I was just talking about. If I put the force right here, which means no eccentricity, the C is going to be equal to what? Number of bolts.
5.
How many number of bolts? I have 5. Cannot be equal to 1. You don't need more information because now you don't have any eccentricity.
Gotcha.
Now the other question I have here for you, let's say we're going to be right here. What do you expect for the C factor? Do you think it's going to be more than 5 or less than 5?
It's going to be less than 5.
Less than 5.
Yeah, less than 5. Okay, good. Let's hear the trends for 1 bolt. We said 1 1/8 of an inch. Let me go back. 1 1/8 of an inch, A490N. Is it single shear or double shear? It doesn't say. This is going to be single shear. 490, 1 1/8 of an inch. This group B, which is mean 490. Single shear is going to be 50.7 for each bolt. So each bolt supports 50.7. I'm going to go here to my C table. I'm going to go back here 1 slide just to confirm. I have 5 bolts. The spacing is 3 inches. Eccentricity is 4 inches. All right. Spacing 3 inches. Eccentricity is going to be how much? 4 inches. I have how many bolts? 5 bolts. Here we go. And instead of having 5 bolts, now I have 3.4 bolts. So what does it mean by that? The strength of the group is going to be equal to 50.7 multiplied by 3.4. Look at this factor. What do you call this factor here? I call it C factor. It's going to be equal to 3.4 out of the table. Just use it here times the strength of 1 bolt. It's going to be 172. Are we good?
Sir, what is S over here and how is it 3 inches?
S is 3 inches. As I said, 3 inches is spacing.
Oh, okay, sorry.
Okay, now let's go here. Where's S? Here's S. The spacing S. And they have to be equal to each other. You cannot go with 4 inches, 4 inches, or excuse me, 3, 3, 3, and all of a sudden you jump to 4 inches. You cannot do it this way.
What if they're increasing in a uniform order? Like 3 inches, 4 inches, 5 inches, then?
Say it again.
What if they are increasing or decreasing in a systematic order? Like 3 inches, 4 inches, 5 inches, then?
No, the two options that you have in the table is going to be S, it's going to be 3 or 6 inches.
I think that would be atypical in terms of construction, right?
Yes, this is typical. Usually people would use 3 inches. In most cases, usually in buildings, we use 3 inches for the spacing. We don't change the spacing. Okay?
Yes, sir. Thank you.
Okay, very good. Then when it comes to seismic connections, we're going to be using which one? Can I use just this for the seismic forces? This table? Just wondering. Can I use this table? You can say no. This table here is for bearing. The other one that you use gave you for slip critical. I'm not including it here. I'm not going to be covering seismic connections. All right? Just so you know. And there should be certain ductility in there and some other stuff that I don't want to cover now. But also in connection, just so you know, if you are going to be pulling this piece here, which is a block shear, I want you guys to know about it. What is a block shear? Let's say that this is going to be like a brace and this is going to be a gusset plate. Now you'd like to pull this out. When you pull this out, you can have more than one mode of failure. The first mode of failure, and when you shear off all of these bolts, you just cut them. So it's going to be one. The second one is when you have tension failure throughout this plate, like what you have done. The third mode of failure, when you have tension failure throughout this section here of this gusset plate. There's more modes of failures, if you like. One of the modes when you have this block shear. And this block shear, what's going to happen? This plate is going to be cutting off this way, like the way you're looking here at. Failure is going to happen through this side of the gusset plate is going to be in tension. Look at this. This is going to be all in tension. And along the sides is going to be all in shear. This is exactly what you call here block shear. You're going to have a combined effect of some shear failure on the side. You can say here is going to be shear failure. And here also is going to be shear failure. And here is going to be tension failure in this phase. So we call this block shear. You're going to see it later on in beam connections. It's going to be very typical in building beam connections. Now let's move here. Now we're done with bolted connections. Now we're going to be moving here to welded connections. And in welded connections, we're going to have a few different types of welding. If you're doing gravity welding, you're going to be following this AWS, American Society or American Welding Society. And the document is going to be this one. Just remember this is going to be D1.1. If you're looking for any information about this welded connection, you need to come here to this one here. If you're doing seismic connections, you're going to be following AWS D1.8. When it says here slash D1.8M is going to be metric, and 2016 is going to be the year that we use. So look at, it's going to be for seismic requirements. Now the welding process. What we care about is going to be the welding threads, but you need to understand the difference between welding and soldering. I'm wondering if someone can explain to us the difference between welding and soldering, if you guys have an idea about it.
Welding is done when we join two plates or when we melt metal to join them. Like the metal from one plate is melted to join the other. Soldering is when you use a third metal to join two metal objects. Usually
Okay.
a small wire or a small connection is used for soldering.
Okay, generally speaking, if you're doing structural steel, it's got to be welding. Soldering is going to be for small pieces when you're kind of soldering a wire to maybe to a connector or something like this that you don't really need to melt the base metal. But welding, you need to do the fusion. Fusion means that you're going to be mixing the two, the welding material, and you're mixing the base material, which means the steel together. And there is more than one method of doing it. So what you're trying to do here is you're trying to heat this up. You're trying to create lots of heat at this location and then provide the welding material in here so that you do this fusion. The welding material itself is brittle, very brittle. It is not ductile like the steel itself. This is why you don't want to use it in seismic connections. You like to avoid this brittle failure. And the ultimate strength for the metal itself, for the welding material, is going to be 70 KSI. So the electrode itself, it says E70. This is going to be the one that you are going to be using. This is a common one. It's going to be this 70. I have here a few links for different videos. You can see here's the first two that maybe we need to watch together. This 4 different videos. I'm going to say part 1, part 2, and part 3, 4. I just let you here enjoy it later on whenever you have time. The good thing, you can just click on this and then you can watch it. Let me show you what I'm talking here about. Let's give you the first one. And this is kind of fun when you watch it. Do you guys hear it? Do you hear? Do you hear the video?
No, not
No,
yet.
I don't.
No.
Okay.
No, not.
Now you should be able to.
And in typical practical engineering fashion. I'm a welding newbie and currently absorbing anything I can on the subject, so while I learn, I thought I would take the time to boil down some of that new knowledge and share it with you. Now, this is welding for the guys and girls at the front of the class who never set foot in a machine shop. You know who I'm talking about, the marching band members, the geeks, the nerds. We're not going to obfuscate things with bumble fudgery and Canadian syllogisms. In other words, if you already nail the keyhole on your root pass, this video might be just a bit elementary.
Good grammar and spelling are important, but if you want to write essays that inspire,
This is unexpected.
messages.
I'm Grady, and this is Practical Engineering. On today's episode, we're talking Welding 101 for hobbyists. For our purposes, we'll define welding as a way to join metals using fusion. That fusion is what makes welding different than brazing or soldering. When you're joining metals, you have 2 parts, the base metal and the sometimes optional filler metal you use to reinforce the joint. With brazing and soldering, the heat is only enough to melt the filler metal and not the base metal. This is the metal equivalent to how most glues work. With welding, on the other hand, the base metals are melted so that fusion can occur. The 2 metals actually become one. Set your spirit free, it's the only way to be. Little Spice Girls reference for you. In general, and compared to other common building materials, metals have excellent mechanical properties. They're hard, tough, strong, and durable. As someone who, and I hate to say it on a welding video, occasionally works the wood, even I can admit that metals are a superior material in many regards. So you can see why it would be advantageous to have a way to connect them together, especially. Welding requires 2 essential ingredients, heat and protection from the atmosphere. The heat, of course, is necessary to melt the pieces of metal being welded so that they can fuse together. The shielding is necessary because molten metals easily oxidize and absorb atmospheric contaminants. These impurities will weaken a weld or prevent good fusion altogether, so some kind of shielding is usually required. Now, there are a lot of ways to make heat. That's actually a fundamental law of the universe, but it's also true in the more specific sense here. So, as you can imagine, with only those 2 basic requirements, a litany of welding methods have been developed using different permutations of heat and shielding. Luckily for me, as the writer of this video, only a few of those methods are widely accessible to hobbyists. Today, we'll talk briefly about 5. The first is Oxy Fuel Welding, also known as gas or torch welding. In this method, the heat comes from the combustion of a mixture of pure oxygen and some other gas, usually acetylene. This combination creates an extremely hot flame which can exceed the melting point of most metals. The shielding comes from the flame envelope, and gas is generated by the combustion, mainly carbon dioxide. With Oxy Fuel Welding, you use the torch to generate a puddle of molten metal. With your other hand, you add filler metal to the weld. It's a very simple process and one of the oldest methods of welding. Advantages are that it feels really awesome to hold an oxyacetylene torch, it doesn't require any electricity, and the torch can also be used for other purposes like cutting, so you can get a lot of use out of a single tool. Disadvantages are that you have to have 2 high-pressure tanks of flammable gases nearby, and the torch is kind of unwieldy, which leads to slower and less consistent welding. For the next 4 types of welding, the heat comes from generating an electrical arc between an electrode and the metal. You've got the short I-sound nicknames, Stick, MIG, and TIG, and I'll sneak flux core in next to MIG, since you can usually use the same machine for both processes. Probably the most common type of welding is shielded metal arc welding, also known as stick welding. This process uses a power supply to maintain an arc between the electrode and base metal. In stick welding, the electrode is also the filler metal, and it's surrounded by flux which melts during the welding process. When an arc is struck, the heat generated melts both the base metal and the electrode, causing them to fuse together. The flux coating also disintegrates, generating both a shielding gas.
You guys have any comments on this video? I'd like to hear from you. I have a very interesting here video for you. This reminds me with the Disney videos.
Shielded arc welding is usually accomplished by means of an electric arc formed between the work and a coated metallic electrode. Let's see what happens. When the arc is struck, it almost instantly creates a temperature of about 6,500 degrees Fahrenheit. This melts both the base metal and the metal in the electrode. The metal from the electrode is melted off in tiny droplets.
This is completely
It's carried
Disney,
across
Disney
the arc
stuff,
and
right?
mixed with the molten base metal. The force of the arc and the forward travel of the electrode causes the mixed molten metal to be pushed to the rear of the crater, where it cools to form a bead. The movement of this metal toward the rear of the crater and the depth of the crater are an excellent check on the quality of the work. The operator should learn to use it as his guide. At the same time that the metal is melting, the coating on the electrode is being consumed. This takes place slower than the melting of the electrode, which shields the...
You guys see, this is just continuous, never stops. Like same as Disney movies in the past.
Really well animated.
And helps direct the flow of metal. It also permits the use of higher currents, with the resultant faster deposit of weld metal. A gas is formed, covering the arc with a protective
I
shield.
should thank him for this presentation, and now we go back to our business here. So what happened?
Sir, before we start, they said that we need to have some covering when we are welding, right?
Cover the weld, meaning cover your face or cover the weld itself?
No, cover the weld itself.
No, you don't cover it like from close, but you need to have protection because you can't
Yes, sir.
just cause
So, sir,
a
many
fire.
times welding is also done underwater, as they showed in the first video's picture.
Yeah,
So, how do they cover that welding? Because water can easily.
I'm familiar with welding in buildings. I'm not familiar with welding below water. I'm not, I
Okay.
cannot call myself a welding expert to answer this question.
Okay.
But as a structural engineer, as they say here, what you care about is gonna be this, is gonna be the approved connections and the trends of the weld. So if I may go back here, the engineer is interested in the resulting weld and in the trends of the weld. So I'm just interested in looking at the weld after they're done, if I have some experience, right? We evaluate some welded connection by visual inspection, if you like, which we call here VT, or I also need to know how to do the calculations and the weld strength.
Okay.
All right, so looking here at different type of welds. We call this fillet weld. Now the weld is gonna be this piece here, right? It's gonna be this piece also. You call this plug weld. So you put the two plates on top of each other, you create a hole, and then you start to put the welding material. So the weld is gonna be welding the bottom plate to this plate. It is very common to use this metal deck attachment between metal deck and between steel beams, or you can do the studs. So it's gonna be either the studs or it's gonna be the plug weld. Also, you can do the slot weld. Slot weld means that you're gonna have horizontal distance here, right? And you're gonna provide the weld there between the two pieces of metal. The groove weld means that you're going to be cutting a piece of each side. It's going to be like V shape, and you're going to be providing the welding there.
Sir, aren't on these types soldering, because we are using a third method to join them,
A third
not the
method?
base plates. Yes, sir. Especially in plug welding, we just make holes and then we use some other method, a third plate, and we melt that and fill the vents.
This is very common when you have metal deck that you want to attach to some steel sections. But it is not common if you like to attach two plates to each other. Just the illustration is shown this way, but it is not common this way.
Okay.
All right. So if you like to do here this complete, if you like to call this to be complete, right? Because this is going to be the welded two pieces. This is one plate, here's the other plate, like what you're looking here at. So what you're doing here full welding, and they call this butt welding. This is going to be full penetration, right? Because you're interrupting the entire plate here and just provide the welding material is going to be here. In order for you to do this, you need to put backing plate. So this backing plate is not part of the weld, and later on you can knock it off. And actually this is what you have in this 4 videos. You're going to see exactly how this is going to get done. How do you do complete penetration weld? We call it CP weld. And this is going to be here, this is like the fillet weld, right? And you see here that usually takes a little piece of the metal itself because of the fusion effect. You're going to be heating the steel plate or the steel material so that you provide here full connection between the weld material and between the steel metal itself. As you see here, this is what they call complete penetration or complete joint penetration. We call this complete CP, complete penetration. So you're interrupting the entire material and you just do the connection. Here we call partial pin connection. And as you see here, you're not really cutting the entire thing, the entire plate, and you're doing here partial pin welding. This complete penetration welding, you don't need to do any analysis to it because you can maintain the strength of the plates. If this plate has a grade of 50 and you just do the full pin weld, you don't really need to do any calculations to prove to us that you have enough strength because you have it already, because this material is stronger than the plate. But in here, you may need to do some calculations if you like to maintain the full strength of the plate throughout. Advantage of complete penetration, as it says here, no calculations, is going to be also simple because you just cut the entire thing and then you provide welding. So it's going to be simple for you, but not simple for the welder. For the welder, it's going to be lots of work. And also here, the preparation here is going to be simpler than this preparation. Here, the preparation is going to be for a certain thickness of the plate or certain, you can say, portion of the plate. But here, it's going to be just cutting the entire plate on an angle. So I'd like here to get to the analysis and also for the full pin use. This is going to be for a moment frame. You'd like to connect here the beam to the column and you need to provide full pin. Because when it comes to seismic analysis, we're going to do this later on in our lectures. We're going to see exactly the reason that we are going to have here full pin, because the entire force or tension that you're going to have in the flange, you need to transfer it completely to the column flange. So we have the bottom flange here of the beam, which is this piece. You have full tension force. You want to be sure that's 100% transfers to the column. This is why you provide here full pin. As you see here, it's going to be full pin welded. This shows here the partial pin weld, how it's going to get done, what angle, and the root, and the depth of it. I'm going to skip this. I don't really need it. The fillet weld, what does it mean by the thickness or the root thickness of the weld itself and the throat. And just so you know, the throat is going to be what we really need to do in our analysis. We need to know the thickness. And if you call here 1/4 of an inch thick, now guess what thickness are we talking about? Are we talking about this width or this width? Which one is going to be the weld thickness? It's going to be this distance or it's going to be this distance. Which one is the weld thickness? It's going to be this guy or this guy? The throat or this? If you like to see here the weld thickness, you're going to be measuring some distance. You measure the distance from here to there, or you measure this distance. Anyone can answer? Right. Don't worry about it. It's going to be this distance here, this length. But what you really care about, what's going to be the effective, is going to be the root, right? The root is going to be this distance here. This is going to be the weld thickness. It's going to be the root thickness. And this is simply is going to be equal to roughly 70% of this thickness. So the root is going to be roughly 70%. To be exact, is going to be square root of 2 divided by 2 is going to be 0.707 times the weld thickness. Okay. Minimum size of fillet weld, it depends on the plate. And here's going to be the minimum weld thickness. I'm going to be skipping all of this. Now I'd like to get to the calculations, which is the important thing for me. Here is the weld thickness, and this is going to be the effective thickness, which is the throat, if you like, or the root. This is going to be the root thickness, but this is going to be the actual weld thickness that you specify in your analysis. So for example, when I say here 1/4 of an inch, I'm going to say here 1/2 an inch weld. This is going to be the distance, it's going to be 1/2 an inch. I have one simple equation here to do the analysis for this, and here's a simple equation. I'm going to go here to the next page. This is going to be your equation here to figure out the weld strength. I guess I'm going to stop here. So if you like to leave, you can go ahead, sign out. If you like to stay with us, stay for questions.
Hi, Professor.
Hi.
I came in late, around late. I was wondering if you marked.
Note
So again,
section
for your question
6.
on this topic, which is the connections, is not going to be included in the exam. The exam is going to stop at slide set number 6. So right before this.
Okay, and the questions that were on the submitted, can questions like those be also included in the exam?
Like what question the submittal? The submittal has a few questions, right?
Yes, like question number 4 or 5.
Can you tell me what is that about? Can you simplify it for me?
Those are for composite beam members.
Oh, you mean design of composite members?
Yes, sir.
Yes, it's given the exam. Absolutely.
Okay. And when will you upload the solution of the submittal?
Solution submittal is going to be different from a person to a person, but I'm going to submit some guidelines on how do you design composite beams. And you know, it's not going to be that much different from the slide sets. So if you really go to slide set 5 and 6, it should cover the exam, the submittal. If you go here to the slide set 5 and slide 6, it should be very good. So even without the submittal answer, you should be fine in doing your exam.
Okay. And sir, during the exam, when you use Proctoring, and can we open the slides or not?
I'm working on this. I'll let you know for next time, but definitely yes, because I'm planning to do it like an open book exam.
So we can use the slides and we can use our electronic
You can use the
books.
slides. You can use the slides. You can use, but I would rather have you guys have it printed in a small size. And I know that you have this, right? So if you like to print it this way, and you can use your steel manual, but you're not supposed to use your phone. You're not supposed to communicate with others via the internet or email or phone or discussion or any of that.
Sir, some of us have the steel manual in electronic form on our computer, so we can use that, right?
Well, I'd like to hear from more than one person. Do you have a printed copy or electronic copy?
Sir, I have an electronic copy. I don't have a printed copy.
Okay, all right. This should be fine then.
Okay.
Professor?
Yeah.
I have a quick question about bearing stress, right? Are we talking for bearing stress, you know, it basically just translates to your shear stress, right? But is it only when gravity loading that you'd have that bearing stress? Like you'd have that little, okay. And then with seismic would be the pre-tension. So, right, so there wouldn't be that little gap.
Yes.
Okay.
This is your design, but in reality, of course, the gap is going to be getting closed, right? Because in reality, the force may get over your design values.
Okay.